Okay, what is a tree? A tree is one of the type of data structure. It is a nonlinear data structure, and also it is a hierarchical relationship between its element without any cycle. And tree is as simple as you know. This is it looks like a linked list, but we have no more nodes. And tree looks like this, okay? And we have a top node, which is the root, which is the parent of all nodes, okay? And under these nodes we have a children's, which are the what we have, is the n3 and 2, which is the children of this node, and this node also their children, okay? And you can see this is all, and this is this node, which is the root node, okay? And this is root node. And if you see here, every node has their, and if you see here from the parent to the children, we have a link. It looks like a linked list, okay? And these links, these are links, which are the link of parent to between the children, which is the edge, okay? And which is the edge I'm going to write here. And if you see here, we have 3 nodes, yes, which is the child of 2 nodes, but they don't have any child. It means whenever they don't have any child, they are a leaf, okay? Leaf. I'm going to write here. And which is the leaf, which is a node which doesn't have any child, okay? And which is these 3 nodes, okay? And also we have an ancestor, which are the, each node, for example, you see here, and we have ancestor of n4, which is the n2 and n1. And also you can see the ancestor of n3, which is the n1, ancestor of n2, which is also n1, and just ancestor of n6, and which are the n3 and n1, okay? Which are the, I'm going to write here, ancestor, and which is the parent and grandparent and great parent, and looks like this. And also we have a next terminology, which is the sibling, and which is the child of same parent. And you can see here, which is the sibling, we have a n4 and n5 also sibling, n2 and n3 also sibling. We have one parent and we have 2 children, and they are the same, okay, the same of this parent. Also we have, this is also, and this is the sibling and sibling, okay? And also we have a depth of node, which is the depth of node, which is, I'm going to write here, and which is the depth of node, and the depth of n3 and 2 node, which are the 1, okay? And from the root to the node, and what is the path of length, which is the 1. And also we have you can see here, and n4, which is the depth of n4, which is the 1 and 2, okay? And you can see here a length of the path from the root to the node, okay? Whatever node we are going to know about it, okay? And this is the depth of node, and also we have a height of node, which is, I'm going to write here. And you can see here, which is the height of node, and length of the path from the node to the deepest node. And you can see here, for example, which is the height of the second node too, okay? Which is the 1, okay? Which is the one we have only one path to the deepest node. And also we can say we have from the root, from a height of the root, which is the n1 to the deepest, which is the path, we have a 2, and also n6 also we have a 2, and this is how we are, from the top to from the node, whatever node, if for example, if the root node or this node, from the node to the deepest node, what is the path, what is the length of path, we are just calculating this, okay? And also we have a depth of tree, and the depth of tree I'm not going to write, which is the same, this one, and depth of tree looks like this tree, and depth of tree always are 0, okay? Because a depth of node, which means from the root to the to the node, what is the path of it, okay, we are counting. But whenever we spoke the tree and we are looking the root, okay, we don't have any nodes up to the node, okay, up to the root. Therefore the always, and depth of tree always is equal to 0, okay? And also we have a height of tree, which is the height of tree is from the root to the deepest node, okay? And we are just counting what is the length of path from the root to the deepest node. And it looks like a node, but here, and we are just looking at the tree, which is the first, which is the parent node, okay? In this case, and the path of length, which is a 2, and here also 2, okay? And it looks like this. And this is all about tree and how it looks like. And also, and tree in the real world, we are using much, okay? For example, in your computer, all file and folders, inside the folders nested in files are also tree, okay? And also whenever we are writing code, yes, in the terminal, and this is our code executed, and this on the terminal also is a tree, and designed based on tree. A tree is a nonlinear, and it means they are hierarchical, okay? And for implementing to the search engine, yes, it is very efficient, okay? And it's very best for searching data from the our tree, okay? It's very and fast. And also, you know, and tree, we have some type of tree, and this is which is the simple, which is the general tree. Whenever we spoke about it, okay, we have multiple nodes, and you know, we know this is the from the root, from the parent and the child. We have a children, okay. We may have a lot of children in the general nodes, and but you know, we have some type of nodes which are the binary tree and binary search tree, evil tree and binary heap tree, yes, and a trie. And these are also tree, and but some of the difference between the general tree and which is a simple tree. And in this video we're going to speak about the general tree, and we're going to create this, and also we're going to speak about the binary tree, binary search tree, okay, what are the type of binary tree and what they are the binary search tree, okay. And let's switch to the VS Code. We're going to create our general tree, which is a simple tree. Okay, we're going to create our tree data structure based on Python list. Firstly, I'm going to create the class for tree, and inside I'm just initializing my tree based on list. I'm going to give the self and also data and also child, and child is equal to empty list, okay, here. And inside I'm going to write the self dot data is equal to data, and then the self dot child is equal to child, and like so, okay. We just initialize it our tree based on list, okay, here you can see. After that we're going to create the next functions, which are for iterating our tree. We're going to create the str function, and also for adding child to our tree we're going to create a child. And firstly we're going to create str functions, def underscore str, and this is str, which is the Python standard operator, okay. And we're going to give the self, and also I'm going to give the level here, and by default is equal to 0, okay. And firstly, and whenever we are iterating our tree, you know, we spoke the tree are firstly we have a parent and also we have a child, it's okay. And for, you know, for easily analyzing our data, which are the parent, which are the child, okay. And we're going to create the variable inside the function, which is the red, and it helps us for analyzing which one is parent, which one is child. We know that our tree is nested, you know, child and child and child. Therefore, for analyzing clearly and seeing what is the child, what is the parent, it is, you know, it's some difficult if we are printing, for example, what is, for example, maybe it's just printing every time we are data, okay. We are just taking the node and we are just printing, but you know, and there is no, automatically it will not print which are the parent, which are the child. But for, you know, knowing that which is the parent, which is the child, we're going to use the level, okay, because, you know, and the first level is 0 level, which always is a root, which is the root node. And after that, whatever we're going to create, whatever inside it has the child, will be the first, which is the 1 level. In the 1 level we have a child of the first root, is the parent of child. And using this level we're going to just analyzing easily, and therefore I'm just defining the red variable, and this variable is especially the empty. We're going to give 2 space here, and then after that I'm just multiply the level, and then I'm going to plus, I'm going to add firstly we're going to create a string, and I'm going to write a string, and here inside the string I'm going to give the data, which is the self dot data, okay, and like so. And after that, whenever we took data, and after that we're going to break the line, and plus we're going to break the line using the backslash and n, okay, and using this. And this variable, every time we are iterating our tree, we are just adding to this red variable, okay. And every time, you know, we are taking data, and after that we are just break the line every time, and we have a huge string will be our, okay. And let's we're going to iterate our tree using the for loop. Every time I'm going to take the child in the self dot child, okay. And every time I'm adding to the red, plus equal to, which is the firstly we're going to call our child. We're going to, you know, we're going to take this child, okay, which is this child, and I'm going to write here child, and then here we are recursively call our function, okay. Recursively we're going to call our dot underscore str, and here again I'm going to give the level, okay, and I'm add 1 every time, adding 1, okay. And whenever it will be, firstly we're going to call this first the first level, and after that will be recursively call our function, okay. And the next time will be the 2 and 3 and like so, okay. And after that, outside the loop, I'm just return that red, okay, that variable. and this is our str function for iterating our tree data structure. Okay, and also we're going to create a last function, which is the adding child to our tree. Okay, and firstly we're going to define the function and the add child. Okay, and especially we're going to write on the parameter itself, and also we're going to write the tree, and after that inside the function I'm going to write the one line of code, which is the self dot child, and this child, this child is the list. Okay, we defined the empty list. Okay, every time we're going to append using append function, we are adding using append function, and that is that tree. Okay, that tree, and that is all about append function for for adding child to our tree. And also we're going to check our tree data structures. Firstly, I'm going to create the instance of tree, which is a tree is equal to a tree, and firstly we're going to give here the what is the root node, which is the, and here I'm going to give the book. Yes, books. Maybe I'm going to create the books of tree data structure. Okay, and after that I'm going to give the empty list, and inside we're going to create the multiple childs, and inside on the books parent we're going to create the 3 child, which are we have a type of books, for example classics. Yes, and just the classics. This one is also going to create 3, and we're going to give here the classics. Yes, and also, and here I'm going to give the empty list. Okay, and also we have a detective books. Yes, or type of, I'm going to create a detective, and is equal to 3 inside the detective, and we're going to give the empty list. And also fantasy, also you have fantasy, and this one also 3 fantasy, and like so. Okay, and we're going to give the empty list here also, and this is our child of this book. Okay, and these 3, and this is the type of books, this is the type, child of that book. Okay, for adding to this we're going to create we're going to write the tree, and we're going to call the add child, and we're going to firstly we're going to give the classics, and also we're going to give fantasy, and fantasy, and also we have a detective, and like so. Okay, and we added to this we added our this 3 child under this parent. Okay, and we're going to see, and first we're going to print our tree, and let's see it. Open a terminal and write the python tree.py, and like so, and you see there is the we printed, and which is this is the root and the parent of this 3 node. Okay, and we're going to create also the child of this 3 node. Okay, and for doing I'm going to, and for what kind of book we have, firstly for classic books, and we can maybe the beloved, maybe. Okay, beloved. Yes, the beloved is a classic book. I'm going to create the beloved, beloved, one of the classic book, and the 3 beloved, also empty list. And also we have what kind of detective. For detective books we have a Nightfire. We have the Nightfire book. We have I'm going to write the Nightfire. This is also 3 inside of the Nightfire, and like so, and also empty list. And also for fantasy we have a Nin's house. Okay, I'm going to write the Nin is equal to 3. Inside I'm going to write the Nin's house, and like so, and also empty list. And also we're gonna we created 3 books. Okay, for classic we're gonna add to this 3 child to this of this nodes. Okay, and firstly for doing this I'm gonna call the classics dot add child, and I'm gonna give the beloved. Okay, beloved, and also I'm gonna call the detective dot add child. I'm gonna give the Nightfire, and also we have a fantasy. I'm gonna call the child, and also we're gonna give the Nin's house, and like so, and save it and open the terminal. And you can see here we added successfully, and which is the classic. We have a books inside. We have a 3 type of books, 3 child, which is the classic, fantasy, detective, and also inside we're gonna
have one child of this. For example, classics has one child, which is the beloved, and also fantasy has the one child, which is the nin's house, detective, the nightfire. Okay, and this is our general tree and a simple tree. Okay, how it looks like.
Okay, let's gonna speak about the next type of tree, which is the binary tree. Binary tree is the most commonly used tree data structure, and it is a we spoke a tree, yes, and a tree we have a one node on the parent node, and then we have a unlimited children. Okay, we have for example 10 and 100, which is how many children we want we can give. But in the binary tree it is not. We have only maximum, we have 2 children only, and 1 or 2, and it looks like this. For example, we have a one, this is the root, yes, and the root, and in the under we have only 2 children, and we have only, and here we have only 2 children, and we cannot have 3 children like this. We don't have. Okay, it is not possible. Each child has their own 1 and 2, maybe 1, and then like so, and 1 and like so. Okay, and we cannot have, it's impossible to have more than 2 children on the binary tree. Okay, and binary tree also divided to many types, which is the 4 types. Okay, and for the first type is the binary tree, which is the full binary tree. Full binary tree, especially we have a one node, yes, and we don't have, for example, in a full binary tree, and we have a node, yes, the root node under, or maybe we have a 2 node, 2 child, yes, and or maybe we don't have any child, and we don't, in the full binary tree it's impossible to having 1 child. Okay, and we have only 2 child, or there's no any child. Okay, each node has their own 2 child, there's no 1 child. And this is, for example, if like so, this is not full binary tree. Okay, and full binary tree we don't have, it's impossible to having 1 child, only we have a 2 child, or there is no child, which is the leaf. Okay, and also we have a 2 child and looks like this. This is our full binary tree. Okay, and okay, next type of binary tree, which is the perfect binary tree. And the perfect binary tree we have especially a node, root node, and they have the same 2 child, and also here each node has the 2 children, yes, and their child, which is the leaf, are located the same level. Okay, if like so, it is a perfect binary tree. It means. Okay, and for example, and if you have a like this kind of tree, it is not a perfect tree. Okay, but we have a 2 child, but the leaf, which is the leaves is not located in the same level. Okay, it means this is not perfect binary tree, but if their leaves, okay, is located in the same level, it means this kind of tree is a perfect binary tree. Okay. Okay, the next type of binary tree, which is the complete binary tree, and we have a nodes, yes, and this node has their own child, and if you see here, each level is complete except the last level. Okay, and the last level is the left side, which is the left, and the nodes and its child, and which is not completed. But it's called the complete binary tree. Okay, but if I change here, and if like so, for example, if like so, it is not a complete binary tree. Okay, and this child always is located on the left side. Okay, must be the left side, and if like so, it is a complete binary tree, except the last level is not complete. Okay, if like so, this is the complete binary tree. Okay, and next type of binary tree, which is the balanced binary tree, and let's gonna see, and you have our nodes, and if you see here at each leaves, which is each leaves is located the same distance from the root. Okay, from the root. For example, this leaves is located, which is the 2 paths, and this leaves also 2 paths, and this leaves also 2 paths. If like, for example, I have 1 child of this node, if this is not balanced binary tree. Okay, but each leaves must be located the same distance from the root. Okay, this is all type of binary tree. Okay, we have a 4 type of binary tree we're going to use in our binary tree. Okay, and before inserting, before deleting, yes, before searching from the binary tree, we must speak about how we can traversal our tree, how we can trade. Especially we have a 4 type of traversal, which is the pre-order, in-order, and post-order, and level order. And the first type of pre-order traversal, and if you see here, I have a tree, and for using the pre-order traversal, we need to traverse from the first root and the left subtree and the right subtree. Okay, and firstly, it looks like this. Firstly, we'll start from here, and firstly we're gonna come here, yes, and then we will go to the right, which is the left side. Okay, and then we can the left, and we're gonna go like this, and we're gonna go here and here, and like so. Okay, and firstly it will be the right side and the left side. Firstly, it will be our left side, and we're gonna go left side, which is we're gonna, whenever we reach the leaf, and then we're gonna look at the right side, and then we're gonna go to the right side, and we will have the, if you will have the left side, we'll go there. If not, we'll go the right side. Okay, and then it will be continuously like this. Okay, I'm gonna write here how we can go. Firstly, we're gonna go n1, yes, and then which is the root, and after that left subtree, which is the n2, and n2, and after that I'm gonna go the, and which is the n4 here. I'm gonna go n4, and after that we reach the leaf, and then we're gonna iterate our, which is the n5. I'm gonna go n5, yes, and then we reach there, and then we're gonna go the, which is the right side, which is the right subtree, which is the n3, and we're gonna go to the, which is the last one, which is the n6 and n6. And this is how it looks like pre-order traversal. Okay, next type of traversal, which is the in-order traversal. And in order traversal, we're gonna start from the left subtree, and then we're gonna go to the root, and then we're gonna go to the right subtree, and we'll start iterating from the left subtree, which is the deepest node, which is this one. Okay, from here, and I'm gonna write how it looks like. And firstly, we're gonna start from the n4, yes, n4, and then we're gonna go the n2, and we're gonna go the right, okay, which is the right n5. And we're gonna go the, and then we finished this, and we're gonna go the root, which is the n1, and after that I'm gonna go the, I finished this, yes, left and the top, and after I'm gonna go the right subtree, and the n3, and also n6, the last one. Okay, if I have the, here is the 1 tree, I will start from here, and then for example maybe the x, yes, and the x, and I will go n3, and I will go n6. Okay, and in this case we don't have an nx, therefore I'm just, if you don't have, we will start from the n3, and then we're going to go the right subtree. Okay, and this is about in-order traversal, how it looks like. Okay, we're going to speak about the next type of traversal, which is the post-order traversal. Post-order traversal looks like, and we know from the left subtree, and then the right subtree, and then top, which is the root. Okay, and it looks like this. And firstly we will start from here, which is the n4. Okay, and from the here n4, and we're gonna go n5, and from this we're gonna go n2, and then we'll not go the root. Instead we're gonna go from the down. Okay, from here, and then we're gonna go the, which is the n3, and then we're gonna go the top. Okay, it looks like this. If I write it looks like n4, and which is the n5, and n2, and n6, and n3, and n1. And it looks like this. This is post-order traversal. Okay, how it looks like. Last type of traversal, which is the level order traversal, and we're gonna start from the 0 level, which is the 0. Yes, we're gonna start from here, and then after that we're gonna go here, which is the 1 level, and then we're gonna go the next node, and from this we're gonna go here, which is the 2nd level. Yes, and then looks like this. If I write, and it will be like this. Firstly we're gonna go n1, and then n2, and then n3, and then n4, n5, and n6. It looks like this. Okay, this is level order traversal. This level order traversal we are using much, okay, for searching, for inserting, for deleting. Okay, node, we are using this level traversal. Okay, and this is you need to understand good, because we are using much. Okay, and this is our level order traversal. It looks like this. Okay, let's we're going to speak about inserting, and how we can insert to our binary tree. And firstly we're going to use, as I told, we're going to use level order traversal for we need to traverse. Okay, we need to iterate our binary tree, and after that, and each of them we are checking it has a child or not. And for example, whenever we came here, which is the here in the first node, yes, we're going to check it has a child or not. Yes, it has a 2 child, and then we're going to check this one. Okay, here, and it has a child. Yes, it has a child, and but we can add 1 more child here. Okay, and therefore we can add here the 1 child after that. And then at the next time, whenever we are inserting here, whenever we reach here, which is the n2, yes, we cannot insert here because we have a 2 child. Okay, and then we continuously go search, and continuously go, and which is the winner reach, and then we're gonna go here, and then we can add here 2 child. Okay, and we can, which is this one is a new, yes, and then we can add here also a new one, and we can also add here also a new one. Okay, and looks like this. And then whenever we reach, again, if we want to add insert, okay, we will reach, and then we can look at, and here we cannot add, and then we're going to go here, yes, we can add, and looks like this, and then we can continuously insert to our binary tree. Okay, and the logic is looks like this. We are just looking that it has a child and it has a how many live. If it has a 2 child, we cannot add, we cannot insert. If that node has a 1 child, we can insert another child, which is the second child. Okay, and then it looks like this. It is how we can insert to our binary tree. Okay, we're going to speak about the searching. And for searching any node from inside our binary tree, and we're gonna use our level traversal. Yes, we are just we are just iterating from the first. Yes, and else we're going to speak about I'm going to search, which is the n5. Okay, and to the n5. If I'm searching n5, I need to iterate, I need to traverse this binary tree, and firstly we're going to start, and here you're going to come here, and then we're going to every time we are searching, we are checking using the if condition. If this node is equal to this, we can return that node. Okay, and here we're going to reach it is not equal to this one, and whenever we come here, yes, and here it is not equal to, whenever we reach n5, this is equal to this, we just return the which is this n5. If not, we will continuously reach, and whenever we reach the last node, yes, the last node, which is this deepest node, and then if we don't have another node, we just return the, for example, if the value is not, the node is not exist in our binary tree. Okay, if like so. And this is how searching function we can implement to our binary tree. It looks like this. Okay, let's going to speak about the deleting node from our binary tree. And imagine I'm going to delete this node, yes, and n3. And for deleting, firstly, I need to iterate entire binary tree using the level traversal, yes. And whenever I reach the last deepest node, which is this, yes. And after that, I need to update, which is I'm going to delete this one. Yes, I need to update this value from here, which is it is not here at n6. Yes, I'm going to update, which is I'm going to update it, which is n3, which is to the n6. Yes, and after that I'm going to delete, which is that one, this n6. Okay, and you may be interesting why we are updating here and why we are deleting like this. And imagine if I'm going to delete, which is the n2, yes, if I deleted this, we cannot access n4 and n5. Okay, I need to update, which is where is the deepest value, and then with this, and I need to update, for example, this one or this one. Yes, whatever I'm going to delete, and I need to update with the deepest node, and then after updating, I need to delete the last node. Okay, it looks like this, and this is how it looks like for deleting node from our binary tree. Okay, let's we're going to speak about deleting entire our binary tree. Deleting entire binary tree is very easy, and firstly, and whenever we created our binary tree, and we're going to create firstly the left child, okay, which is the left child and the right child, and we have a node, and which is for deleting, we just update our this node for creating, for example, I'm going to give for the root, yes, is equal to none. Yes, and also the left child, which is the left dot child, is also equal to none, and also right child dot child also equal to none. Okay, whenever we wrote this code, yes, and we're going to implement this delete function in the code. Also, we're going to speak about how it looks like. Whenever we wrote this code, whenever we are updating, the root node is none, and the left child and the right child is also none. It means we are just disconnecting this to this node. Okay, it means whenever there is no any reference to this node, the garbage collector will delete entire nodes, entire binary tree. Okay, from this we can delete entire our binary tree. Okay, and this is all about binary tree, how its functionality. Let's switch to the VS Code. We're going to implement all functionality in the code. Okay, let's do it. Okay, let's want to create our binary tree based on linked list. And firstly, I'm going to create the class JSP tree. And firstly, I'm going to define a function. I'm just going to square init, and here it is self, and also I'm going to give the data. And inside, firstly, I'm going to write the self dot data is equal to data, and after that, whenever we're creating our binary tree based on linked list, and the linked list in each node we have 2 pointers, which is the left pointers and the right pointers, which is the left child and also right child. Okay, and here what we're going to define, we're going to just initialize this self dot, which is the first, I'm going to write the left child, and is equal to none, and also we're going to write the self dot right child, and this is equal to also none. Okay, and after that we're going to create our traversal function for iterating our binary tree. Okay, we spoke about all 4 types of traversal, and we're going to create all of them step by step. And firstly, we're going to create our pre-order traversal, and for doing this, I'm just initialize the function diff, and which is the pre-order, and it takes the self, and also it takes the root and the root node. Okay, and inside, firstly, we need to check our root node, and which is we have any node inside our binary tree or not. Okay, if not, just return the binary tree is not exist, something like that. Okay, and if not, just the root node is not, okay, I'm going to return which binary tree is not exist, something like that. Okay, and after that I'm going to just write the print, which is the root node and that data. Okay, and looks like that. And after that I'm going to call recursively pre-order function. Okay, and self dot pre-order function. Okay, and firstly we're going to give the root node dot here, and we're going to give the firstly left child, which is the left child, and here we are just iterating the left child first. Okay, and after that I'm going to get to call recursively one more pre-order traversal, and which is the root node dot right child, and child. For iterating our binary tree, we need to call our pre-order traversal recursively. Okay, and after that we're going to create our next function also, which is the Inorder Traversal. Okay, we're going to create all of them what we spoke on the whiteboard, and in order it takes the self and also root node. Okay, and inside whatever we wrote here, and we're going to write this again. Okay, inside, and just copy and paste, and here we have some changes. Firstly I'm going to cut it, and after this I'm just paste it. Okay, and after that whenever we are in Order Traversal, we spoke about it, and after calling the left child, okay, we're just printing the node. Okay, and also we're going to create the next function, which is the post order traversal. Order, it takes self and also root node, and inside I'm just copy and paste this in the code again, because and the logic, the code is the same, but for printing, it is some changes we're going to change. And after this I'm just print that one. Okay, print, and that's it. Okay, this is our post order traversal, it look like. And also we have a level order traversal. Okay, just want to create this one also, level order, and it takes the self and also root node. The inside, firstly, this will be the first code the same, but after that we're going to change some codes. Okay, and whenever after this I'm going to write the else, and inside else, and firstly we need to import our queue data structure. We're going to use queue for the level of the traversal for iterating. Okay, and I have a queue, and this queue data structure, we created this queue. Okay, and I'm going to import this queue, and I'm going to use in my code. Okay, on the top I'm going to import, and which is the import queue. Okay, and then inside I'm going to use for iterating for level order traversal. Okay, and firstly inside I'm going to create a custom queue, just the custom just a queue, and this is equal to queue dot queue. Okay, and I'm just creating the instance of that queue. Okay, and after that I'm going to call the custom queue dot enqueue, and here I'm just giving the root node. Okay, and I'm going to give the root node, and after that I'm just iterate using the while loop, and whenever is not, which is the custom queue, I'm going to call the custom queue dot is empty. Okay, we have and we have a is empty function in our queue data structure. Okay, and whenever, for example, it returns for example true, yes, is empty, and it is not a true, which is not, I'm going to put here, and it means every time whenever it returns the false, it means, and whenever it returns the true, okay, and our loop will stop. Okay, and inside firstly we're going to define the root, the variable, which is the root. This is equal to custom queue dot DQ. Okay, I'm going to call DQ, and I'm just giving the and for the root, which is the DQ. At DQ it returns the, which is the our variable, which is the deleted, DQ is deleted, which is the first data in our queue, and then return that value. Okay, and we're going to use the root, and for I'm going to just print here, and which is the, I'm going to write just root dot value dot data, and this is we are just printing our data, which is the our, what is the value in our binary tree. Okay, and how it is queue is working. Queue, whenever first in first out. Okay, it means every whatever data in our queue data structure, and first data will, whenever we are using DQ, it delete the first data and return that data, and for using this we are just printing that data. Okay, and after that, and we're going to write our two if condition for left child and the right child, and if just root dot value and dot, here I'm just write a left child. Okay, and is not none. Okay, it means whenever there are left child, we have some data. Okay, and inside, if like so, inside firstly we're going to call the custom queue and dot enqueue, and here I'm just going to give the, which is the root dot value and dot left child itself. Okay, and like so. Okay, we are just enqueuing that value, and after that I'm gonna write the, which is the another if, which is the same, but there is some differences. I'm gonna make changes. Okay, firstly we're gonna change this just to the right, and also we're gonna change this here also to the right, and this is our level of the traversal. It looks like, okay, we are just iterating using the while loop. Okay, every time iterating, and then we are just visiting to the left child and the right child. Okay, we are just enqueuing to our queue data structure, and every time here we are just dequeuing, and we are just taking that value and we are just printing here. Okay, and then let's, we're going to create our binary instance of binary tree, and we're going to give some child to our binary tree. Okay, and let's going to do it. Firstly I'm going to create the b tree. Binary tree is equal to binary tree, and here I'm just gonna, and here I'm gonna give the, what is the root of our binary tree. Okay, and let's gonna give the books maybe, yes, and after that I'm gonna write the, just the left child, and this is equal to b3. Okay, and here we're gonna give the, what is the inside the child, which is the, what is the left child. Okay, and we're gonna give maybe the classics. Okay, and after that we're gonna give the right child, and this is equal to b3, and inside we're going to give maybe fantasy, and it looks like and then after that I'm just calling the b3, and then I'm gonna just update the left and the right child. Okay, and which is the b3 and dot firstly the left child, and this is equal to left child, and also I'm going to call one more time b3 dot right child is equal to, and which is the right child. Okay. And we are just giving our binary tree the childs. Okay, the left and right. Okay, and let's we're gonna iterate by using the firstly Inorder Traversal. Okay, and let's gonna firstly, and we're gonna b3 dot preorder, and here I'm gonna give the root node. Okay, which is the b3, and that's it. And save it and open the terminal, and we're gonna write the Python b3.py, and if you see here, whenever our preorder traversal, it starts from the root and and after that the left child and the right child. Okay, and also we're gonna call our, which is the Inorder Traversal also. Let's save it, and that's what we're gonna see. And if you can see here, and it starts from the left child, and after that the root, and after that the right child. Okay, and our Inorder Traversal, how we spoke on the whiteboard, it looks like this. Okay, and also that's going to call the post-order traversal also. Save it, and run it. If you see here, it starts from the left child and then the right child, and at the end it's the root. Okay, and at the last is the root, which is the how post-order traversal it looks like. Okay, and also we're going to call the last traversal, which is the level of the traversal, and save it, terminal. I made a mistake, I think somewhere. Oh, here. Okay, oh, I made a mistake here, and I need to write the right child. Okay, and save it, and one more time. let's run it. And okay, see it, you can see it starts from the root and then the left child and then right child. It looks like this. Okay, and this is all about traversal. Okay, how we are iterating our binary tree. And then let's want to create our next function, and which is the searching. Okay, how we are searching our binary tree. And let's want to create our search function, and a def and search takes self, and also it is the root node also take, and it takes the node value and this. Okay, and inside firstly I'm going to check, which is the if root node is not exist. Okay, and if node exists, which is the root node, yes. If like so, I'm just return the b3 is not exist, and like so. Okay, and if not, I'm going to write the else. And here firstly, we are just for searching, we're going to use our queue data structure. Okay, I'm going to create a custom queue, which is the custom queue is equal to the queue dot queue. Okay, we're just creating our instance of our queue, and then after that I'm going to call the custom queue and dot enqueue, and here I'm going to give the root node, and after that we are just iterating using the while loop, not custom queue dot is empty. Okay, how we wrote in our level order traversal is looks like this. Okay, if you see here, it's the same how it is. Okay, and we spoke about how we are searching, and the logic is looks like this. Okay, but and after that, inside the while loop, we're gonna check using the if condition. And firstly, and inside the while loop, we're gonna create just the root and just the custom queue dot dequeue. Okay, and after that I'm gonna write the if condition, which is that we are just comparing the root value and with the node value. Okay, which is the if. I'm gonna write the if and the root dot value dot data if this is equal to node value. Okay, if like so, and we're gonna return that node value. Okay, and which is the return node value. Okay, and then I'm gonna write our next condition, which is the how we are wrote here the same. I can copy this for for jumping to the next for the left child and the right child. Okay, and then outside the while loop I'm going to return if, for example, we didn't find this node value. Okay, inside if we didn't find from node value from our inside binary tree, and here I'm going to just write and return node found, and it looks like this. Okay, and let's save it, and let's want to check our binary tree, and let's want to delete this one. Instead, binary tree dot search, and here we're going to give the b3, and also I'm going to give the value, and here that we're going to give the node value, and let's want to give the maybe the class 6. Okay, and class 6. Save it, open terminal, let's run it, and we need to print this. Okay, let's want to print it, save it, and you can see it returns the classic, which is exists now. Maybe if for example I'm going to give just this, maybe yes, let's check it, and you can see it's not found. This is our search function. It looks like. Okay, and also we're going to create our next function, which is the insert thing to our binary tree. For this we're going to create the insert function, and let's going to do it, and for the def and the insert, and firstly it takes the self and also root node, and here it takes the new node value. Okay, and inside firstly we need to create our new node value by using the binary tree. Okay, and firstly new node is equal to binary tree. It looks like this. Here I'm going to give here that is the new node value. Okay, and after that I'm going to check if node root node, and inside I'm going to write the root node is equal to new node, which is this. Okay, and if for example we don't have any node inside, it means the root node is equal to new node. Okay, and whatever we are inserting. Okay, and after that I'm going to write the else, and the code will be the same here what we wrote, Let's going to copy it. I'm going to paste it here. And you know, and if whenever we are inserting data, we are iterating our node value. Okay, we spoke how how we can insert. Okay, and therefore we're going to use the queue data structure for inserting also. Okay, and after that, you know, here I'm going to write the if condition, what we spoke on the whiteboard. Okay, and which is the root, and here the value, and also the, you know, here I'm going to write the left child, and is not none. Okay, if like so, and I'm going to write here the custom queue dot enqueue. Okay, and the root dot value dot left child. Okay, and then we're gonna write the else also, else, and here, you know, firstly we're gonna write just the root dot value, and just the root dot value, and dot here is the left child is equal to new node. Okay, and then we're going to return just the inserted. It looks like this. Okay, and also, you know, that we're going to write our next if condition also for the right child, and this code is the same. Okay, but we need to change that, just the not left to the right, and here also, and here also, and that's it. And let's save it, and let's want to check our insert function. And after this, I'm going to call that one firstly to print, and we're going to call the b3 dot insert, and here firstly we're going to give the root node, which is the binary b3, and after that we're going to give the new node value, which is the maybe, and we're going to give the nins house, like so. Save it in terminal, let's run it, and you can see it is inserted. Okay, if we print, and it's going to print, and I'm going to call the b3 dot level traversal, and b3, and let's going to see it, and you can see here the nins house is added. Okay, and this is how it is looks like. Okay, how it is the insert function is looks like. And also we're going to create our next function, which is the delete, for deleting node from our, you know, from our binary tree. And firstly, for deleting our node, we spoke about, you know, and firstly we need to find the deepest node, and also we need to update with this. Okay, therefore I'm going to create, for before creating the delete function, I'm going to create the, which is the get deepest node function. Okay, and for getting the deepest node. Okay, let's want to create that function first, and I'm going to define a function which is the get deepest and node. Okay, and it takes the self and also root node, and inside firstly we're going to check our binary tree if node root node, and inside I'm just return, and which is the b3 binary tree is not exist, it's not exist, and like so. And also we're going to write the else if not, you know, for we are iterating using the level of the traversal. Okay, and the code is looks like this and this one. Okay, we're going to copy this one, which is level of the traversal, you know, and I'm going to paste it here. And here, you know, the code is looks like the same, but you know, here we are just returning the value outside the code is the same, but you know, we're going to make it some changes, and outside the while loop I'm going to return and which is the root dot value. Okay, we are just returning the root dot value, which is the deepest node. Okay, this is the deepest node. Okay, and let's save it. And also, and for, you know, and for deleting node, we're gonna, and we found, you know, this deepest node, and after that we need to delete, which is the deepest node. Okay, also, and for doing this, I'm going to define the function def delete deepest node. Okay, and here, and it takes the self and also root node, and also it takes the deepest node. Okay, it takes the deepest node, and we're gonna find, if using the deepest node, you know, get deepest node, we're gonna find this variable. Okay, and inside the firstly, you know, the code is looks like this, and just copy it, and paste it in here. And after this, I'm going to write the if condition, which is the if and the root dot value and is equal to, which is the deepest node. Okay, if like so, here I'm just write the root dot value, and which is this is equal to none. Okay, and like so, and after that we're gonna return it, and after that I'm gonna write the next if condition, if root dot value and dot, which is the right child, and if like so, if we have it is not none, I'm gonna inside also we're gonna write one more if condition. Okay, if the root dot value and dot right child and is deepest node, which is the deepest node. If it is, I'm gonna return here. I'm just updating the left or right child. Okay, and which is the root dot value and dot right child is equal to none, and like so. Okay, and after that I'm just return, and also I'm gonna write here the else condition also, and here I'm just calling the custom queue dot enqueue, and here I'm gonna give the root dot value and dot right child, and like so. Okay, and and after that I'm gonna write the next if condition for for the left child. Okay, and the code will be the same. I can copy this code here, and I'm gonna copy, and here I'm gonna change right to the left. Okay, and also here left, and here also left, and the last one also. And this is all about deleting deepest node. Okay, and whenever we updated the deepest node, and for example deepest node, whenever we are deleting some node, we are just updating with the deepest node, and after that we need to delete deepest node. Okay, and we're going to use this function for deleting deepest node. Okay, and after that we can create our delete node function for deleting, and we're going to create that function also, and I'm going to define the function, which is the delete node. Okay, it takes the self, and also it takes the root node, and also it takes the node itself. And inside we're going to check, and firstly the code will be looks like this. Therefore I'm going to copy this and copy and paste it here, and here I'm going to write the root equal to custom queue dot dequeue, and after that I'm going to write the if condition, if and root dot value and dot data. Okay, data is equal to node. If like so, inside I'm going to write that, which is that firstly I'm going to define that, which is I'm going to find the deepest node using the deepest node is equal to, I'm going to call the self dot get deepest node. Okay, we are just getting, and I'm going to give the root node here, and we're going to here here for we are just calling the get deepest node function. Okay, and then we took the deepest node to this variable, and after that I'm going to write the root dot value and the dot data is equal to deepest node dot data. Okay, and after that I'm going to call the delete deepest node function, which is the self dot delete deepest node deepest, and here I'm going to give the root node, and also we need to give the deepest node. Okay, and that's it. And after that I'm going to just return, which is the deleted. Okay, we deleted successfully. And after that we're going to write the two if condition for iterating and our binary tree, and we're going to write which is this code, and which is this code. Okay, and I can copy this, and I'm going to paste it here. And this is the for we are just visiting to the left child, and also we are just visiting the right child. Okay, we are just enqueuing to our queue data structure. Okay, and this is all about the delete node function. It looks like, and save it. That's going to check our delete node function, and here I'm gonna we are not printing this. Okay, and we're just adding, but you're not printing. And after this I'm just calling, and first we're gonna print, and I'm gonna just call the b3 dot delete node, and here I'm gonna give just the root node, which is the b3, and also I'm gonna give the node. Okay, and let's, I'm gonna delete the nins house. I'm gonna give the nins house. Okay, and here I'm just comment this one and save it, open terminal. Let's run it, and you can see here, and we deleted, here, and this is all about the delete function. Okay, and also we have a last function, which is the deleting entire our binary tree, and let's gonna write that function also, which is very easy, and the delete, which is the b3. Okay, and it takes the self and also root node. Okay, inside I'm going to write the root node dot data is equal to none, and also root node dot left child is equal to none, and also root node dot right child is equal to also none. And after that I'm just return, and which is the deleted. Okay, and it looks like this. And let's going to check this function also, and here we're going to write b3 dot delete binary tree, which is this. I'm going to here I'm going to just give the b3, which is the root node. Okay, let's print this one and save it, open terminal, and you can see here we deleted is printed. It means we deleted entire our binary tree. If I iterate my binary tree using the Order Traversal, and you can see there is a none. Okay, because we don't have any binary tree data, and we don't have any data in our binary tree. Okay, and this is all about binary. Okay, let's want to speak about the next type of tree, which is the binary search tree. Binary search tree is the same as a binary tree. Okay, but let's want to speak about what is the difference between a binary tree and binary search tree. We have a node, yes, we have a tree, and in the binary tree we have a the binary tree is also binary search tree is also binary tree, but in the binary search tree we have some more features, which is the first one is, and the left child value is always less than the root value. Okay, and also right child value is always greater than the root value. Okay, and each for example, this is maybe here 50, yes, maybe here is 30, and maybe 70. Okay, and whenever we have inside the child also will be like this. Okay, and we have maybe 60 and maybe 80, and looks like this. Okay, this is binary search tree. Okay, binary search tree is very fast to search any number from the binary search tree. Okay, and for searching, and for example, I'm going to search maybe the 70. Okay, and for searching a 70, whenever we are iterating using the level order traversal, yes, and we need to compare with the root node. Okay, and the root node, if for example the value is greater from the root node, and we will go to the right. If value is less than root, we'll go to the left. Okay, and in this case the 70 is greater than the root value, therefore we're going to go to the right. Okay, and then we just compare with this, and then we can return. If maybe it can be maybe this 80, yes, if like so, we will come here, and also we'll just compare which is the parent with the 70 and which is the 80. If the 70 is less than from which is this 80, if we're going to go to the right. If this value is less than from this 70, we're going to go to the left. Okay, and the logic is the same, and it looks like this. Okay, and for deleting also, if you are going to, for example, if I'm going to delete a 40, okay, from the tree, and firstly I'm going to compare with the root. If this value is less than from the root value, I'm going to go to the left, and then here also I'm going to compare, and this 40 is, if they know the value is greater than this node value, I'm going to go to the right. If not, I'm going to go to the left. In this case, it's greater, I'm going to go to the right, yes, and then we can just delete this one. Okay, for deleting entire binary tree, and we need to update the root value is none, and the left and child is also none. Okay, after that the garbage collector delete will delete all nodes. Okay, and the time complexity in the binary search tree is the log n. Okay, because whenever we are searching any any value from inside the binary search, we are searching as half and half and half. Okay, it means for example, if I have maybe, in this case I have, here 4 and 7 numbers for searching 80. Yes, I need to compare 1 and 2, and then I will compare it 3 times, and then I will immediately reach to that value. Okay, therefore is time complexity log n. For deleting also time complexity log n. Okay, and this is all about the binary search tree. And let's switch to the VS Code. Let's implement binary search tree and based on the linked list. Okay, let's do it. Okay, let's create our binary search tree based on the linked list. And firstly, as like before, we're gonna create class VS tree, binary tree, and inside I'm initializing underscore in it, and in the self we're gonna give, and also we're gonna give data. And inside, firstly, I'm just initializing how I initialize it in a binary tree. Yes, it looks like the same. Okay, I'm just write the self dot data is equal to data, and after that I'm going to write the self dot left child is equal to none, and also self dot right child also equal to none. And okay, we just initialized our binary search tree. Okay, let's create our next functions, which are for inserting, for iterating, and for deleting. Okay, and searching, and let's do it. And firstly, we need to create the let's insert function. We're gonna create, okay, def the insert, it takes the self and also root, and node underscore value. The inside, first I'm gonna write if root node. Okay, we are just checking dot data is none. If like so, I'm just write the root node dot data is equal to node value. Okay, and like, and after that I'm gonna write the if, and which is the node value less than or equal to our root node dot data. Inside I'm gonna write the if condition, which is I'm gonna just now the root node dot left child is none. Inside I'm gonna just write the root node dot left child, and this is equal to bs tree, which is the binary tree. We're just creating instance of binary search tree. Okay, and here I'm going to give the node value. Okay, and like so, and then I'm going to just write the else, and here I'm just write the self dot, I'm just recursively call insert function. Okay, insert, which is the root node dot left child. Okay, left and left child, and then we're going to give the node value. Okay, and like so, and also we're gonna write for the right child also the code is the same how we write. Okay, here I'm just copied it, and here I'm just gonna write the else. Instead I'm just paste it how I copy it. Okay, and here I need to change the left to the right, and also here, and one more here also. And after that I'm just return, and which is the return inserted like so. Okay, and we just inserted our data to our binary search tree. Okay, just save, we can save it, and also let's want to create our, which is the iterate function also, and then we're going to check our binary search tree. Okay, and let's want to create that function also, def, which is the level of the traversal order. Here I need to give the self and also root node. Okay, and inside I need to write the same logic how I wrote on the binary tree, and the logic will be the same. Okay, and you can see here I explain it on the binary tree. Yes, the same logic here is going. Okay, and let's want to create our instance of binary search tree. bs tree is equal to bs tree, and here on the data let's want to give the none. And then whenever we are inserting data to our binary tree using the insert function, and we can insert data to our binary tree. Okay, and let's going to call the bs tree dot insert. Okay, and here we need to give the root node, which is the bs tree, and then we're going to give the node value, which is let's going to give the maybe 70. Yes, maybe we're going to give 60. Okay, and then we're going to insert one more, for example 90, and after that it's 30 parentheses, and after that I'm just iterate my binary search tree. Okay, and using the level traversal. Okay, and bs tree dot level of the order, and I'm going to give here bs tree. Okay, which is the root node here, this one. Okay, and let's save it and open the terminal. So we're going to write the python and the bs tree dot py. Oh, I made a mistake here, which is that whenever we are comparing this
Oh, I wrote the 2, so I made this. Okay, and save it, open terminal. And you can see here we inserted, okay, and also we are just iterated our binary search tree. Here is the which is the root node, which is the 60, and then the left child and the right child. Okay, it looks like this. And we're going to create our next function, which is the search function, okay, for searching any node from inside our binary tree. Okay, and let's going to do it. And firstly, we're going to create the function def search. And here I'm going to give the self, and also we're going to give root node, and then we're going to give the node value. And inside I'm going to write the if root node, okay, dot data if this one is equal to node value. Okay, it means we found it. I'm just returning that is the return found, and like so. Okay, and then we're going to write the else if, and here another node value, and if this is less than root node dot data. Okay, if like so, it means we are just visiting the left child. Okay, and we are just checking the all left child value. Okay, and for doing this, we need to write one more if condition. If root node dot left child dot data. Okay, if this is equal to node value, if like so, just return found. And then I'm just write the else, and we need to call our search function recursively. Okay, and here I'm going to write self dot search, and here we're going to give the root node and dot left child. Let's call it left child, and also, and after that I'm going to give the node value. Okay, and then we're going to write the else here, else, and the logic will be the same, but here in this else, and we need to visit to the right child. Okay, and right child, I'm going to write here also right child. Okay, and this is all about the search function. Okay, and let's save it. After inserting, and I'm going to write here, I'm going to call binary search, which is the search function. Okay, and I'm going to print, and here I'm going to call the bs3 dot search, and here we're going to give the root node, which is the bs3, and also we're going to give the node value. We're going to check which is the 30. Okay, and let's comment this and save it and open terminal. Let's run it, and you can see this is found. Okay, and if we're going to give them maybe the 90. Okay, and let's run it. You can see this is, we found it. And let's want to create our next function, which is the delete function, deleting one node from inside the binary search tree. Okay, and before creating by delete node, we're going to create which is the minimum node value. We need to find it. Okay, therefore we need to write, we're going to create our minimum value node, which is the function, and the min node value. Okay, and it takes the self, and also we're going to give the root node. Okay, and inside we're going to write the node is equal to root node. Okay, and like so, and I'm just iterating using the while loop, and node dot left child is not none. If like so, I'm just in node equal to node dot left child. We are just using the while loop. We are just visiting entire to the left child. It means whenever minimum value, and here you might be interested why we are at the left child, because on the left side the all minimum value, which is the small value, small number, small value is located. Okay, values, and therefore I'm just visiting the left child every time. Okay, whenever I'm iterating. Okay, and after that, whenever I reach to the minimum value, I'm just returning that one, which is the node. Okay, and this is about a minimum value function. And then let's going to directly create our delete node. Okay, delete node. Okay, here it takes the self and also root node and also node value. And inside, firstly, we're going to check our root node. If root node is none, if like so, we're going to return root node. Okay, and after that I'm going to write the one more if, and which is the here I'm going to compare node value to the root data, which is the root, what is the root value. Okay, and therefore I'm going to write the node value if less than, which is the root node dot data. If like so, inside I'm going to write the root node dot left child, and is equal to self dot, we are just recursively call delete node, okay? And if you know here, I'm gonna write at the inside, I'm gonna write just root node dot left child node value, and after that I'm gonna write if, and here I'm gonna compare node value is greater than just the root node, the data. If like so, I'm gonna write here just root node. We are just, you know, and here we are just visiting to the right child, okay? And you can copy this and let's gonna paste it here. I'm gonna change left to the right, and also one more here also, and like so, okay? We are just visiting to the right child, okay? And then we're gonna write the else, and inside else we're gonna check if root node dot left child is none, okay? If like so, inside I'm going to create a variable which is a temp is equal to root node dot right child, okay? And just the right child, and here, you know, we are just, if like for example, you know, whenever is left child is none, and we are just taking, if like so, it means, you know, we don't have a left child, okay? Therefore we're going to go to the right child, okay? Therefore I'm just creating here the temporary variable, and using this temporary variable I'm going to use, you know, I'm just write the root node is equal to none, okay? And like so, and then I'm going to write the return temporary node, which is this, okay? And then we're going to write one more if to the left, and which is the same. I'm just copy and paste it here, and here, you know, we're going to change left to the right, and also we're going to change, and here it will be left, and like so, okay? And then we're going to write the temp is equal to self dot minimum node value, okay? We are just taking the minimum node value, and here I'm going to write the root node dot right child, and then I'm going to write just the root node dot data is equal to temp node temp and dot data, okay? And after that I'm going to write root node dot just the right child, and here we're going to call our delete node function recursively, self dot delete node, and here we're going to give the root node dot right child, and also we're going to give the temp dot data, okay? And then, you know, and actually after that I'm just return and then root node, okay? And here I'm going to return root node, okay? And like so, this is all about the delete node function, okay? And save it, and let's go and check our delete node function, and let's go and cat this one. And after that I'm just write the bsc3 dot delete node, and here I'm going to give the bs3, and also we're going to give, and let's we're going to delete maybe 30, okay? And let's save it, open terminal, and you can see here 30 is deleted. If I delete maybe the 90, let's check it, I can see here is 90 is deleted, okay? And like so, okay? And even we can delete the root node also, which is 60, and you can see here, and 60 is deleted, okay? And this is about the deleting node from binary search tree, and also we're gonna create the last function, which is the deleting entire binary search tree, and we're gonna create that function also, which is very easy to implement, okay? And we just write the full line of code, def and delete bsg binary search. Inside we're gonna give the self and also root node, and inside firstly we're gonna write the root node dot data is equal to none, and also root node dot left child is equal to also none, root node dot right child also equal to none. And you can see here this code is very the same how we brought it to binary tree. Yes, binary search tree also the same code, okay? And then we can return, and bs3 is deleted, and like so, okay? Let's save it, and then let's go and check after this, okay? And bs3 dot delete binary search tree, and here we're gonna give the bs3 and save it, open terminal, let's run it. You can see here none. It means we deleted all nodes from our binary search tree, okay? And this is all about the binary search tree.